Hi, in this video I'm going to show you exactly how we calculate expected shortfall under basic historical simulation. Now, expected shortfall is both desirable and timely. It's desirable because it is coherent, satisfies all four conditions of coherence, including subadditivity, whereas VAR does not. Second, it's timely because you may know that in Basel IV, specifically a fundamental review of the trading book, VAR is being replaced by expected shortfall. So previously, this is more perhaps of academic interest. It is now popular and practical. As a bonus in showing this calculation, I'm going to distinguish expected shortfall from conditional value at risk. Now, I'm aware that they oftentimes are used as synonyms. That's understandable because in both cases we're talking about a conditional average. That is to say, I have illustrated here against a standard normal distribution. In red here, I'm illustrating a 95% expected shortfall, or CVAR if you want to use them synonymously, because we're referring to a conditional average. That is to say, what's the loss we expect if we do end up in this 5% loss tail? In that sense, they are synonyms. But I'm going to show you that the differences between how we define the threshold, and this is what makes expected shortfall better than conditional VAR. Expected shortfall is the conditional average, the average conditional on us ending up here in the 5% tail, if it's a 95% VAR. So the threshold is delimited by that probability of 5%, whereas conditional VAR is based on the expected loss worse than the quantile, but the quantile can actually be ambiguous. That's the subtle technical difference that makes expected shortfall, in my opinion, slightly superior to the conditional value at risk. But I look forward to showing the actual calculations to you here with some simple examples coming up. In order to illustrate expected shortfall for you, I've generated a super simple simulation in this column here that depends only on three values: the initial value of my portfolio, and then as part of the super simple simulation, we're in the mean variance framework where I'm just going to signify the return and volatility of my asset, denoted as usual by Greek mu and Greek sigma. So 10%, we sometimes call that drift. We're expecting to grow by 10% per annum per se, but with a significant volatility at 30% per annum. So here is my simulation. I'm just taking that expected return or drift of 10% and then adding the volatility that I'm shocking or multiplying by a random standard normal variable. So I'm randomizing the volatility. And then this just gives me, this is not a time series here. This is 100 separate trials. There's my count where I'm getting here the change in wealth over the period. So you can see here in this first simulation, it's a $10.16 growth or gain in the portfolio. Second simulation here, $21.97 growth in the portfolio. But because we do have a high volatility here, we do expect to see some losses here in red and parenthetical. So here's a case of where we actually, under the simulation, we lose almost $40 on the position. So that's very simple here. I'm not showing you the whole column, but first, second, third, fourth, and then I can, every time I rerun it, get different values. But my count here is 100. And so I have a set of 100, what we could call profit and losses. And then so my column is mathematically intuitive to us, right? The loss here is a negative and also colored red. But then when I'm going over here, I'm doing something that we oftentimes do in risk, and that is I'm switching from the natural, right here is a P&L. We could say P&L, or if we want to be really specific, we could actually specify the P plus and the L minus This is just to say that the format matches the mathematics and our intuition that profits are positive and losses are negative. However, here I've switched to LP format. We oftentimes do that in risk, convert the losses to positive values, and So I've sorted here by retrieving the worst losses using the small function and then negating it. So the point here is that I have generated 100 series, and my lowest value here, you can actually see it, it showed up for me, is negative a loss of $74.01, or that's mathematically negative 74.01. But then when I represent it in the L positive or the LP format, I'm just using the positive value. So my worst loss among these 100 is $74.01, right? So it's a loss off that initial value. My second worst is $50.55, and so on. So just using the small function, I'm retrieving them in sorted order from worst to last, where I'm representing a negative as a positive, consistent with what we call LP format. Now, what if I wanted to say, what is the 95% confident value at risk under this simple historical simulation? And by simple, one of the things I mean, or what I especially mean, is that we're giving equal weight to all of these losses, because we do have more advanced variations on this equal weighting. But here, I think we can all agree that it's just natural to explicitly or even just implicitly give each of these losses the same weight. And I ask, what's the 95% value at risk? Well, actually, there is more than one value. There is more than one valid answer. So we say that 95% value at risk under this basic historical simulation where the distribution is discrete, we say that it's actually ambiguous, because it's reasonable for somebody to say, we have 100 after all, 1, 2, 3, 4, 5 out of 100, 5%. This must be the VAR, $40.59. It is reasonable. However, following Kevin Dowd in the FRM, we actually say it's the sixth worst, would be the 95% VAR if there are 100. So I would actually say it's $38.13, and then someone else could come along and explain why. That, to be more precise, we would interpolate between the fifth and sixth values. So 95% VAR is ambiguous because in this case, where the count is of 100, acceptable answers include the fifth worst, by the way, consistent with Philip Jorian, the sixth worst, which is our default answer in the FRM, and an interpolation, which is a sophisticated way to approach it. And so that's a weakness of VAR, we could say, as far as being a metric in this discrete distribution, but expected shortfall never suffers that weakness. Expected shortfall is a conditional average that is delimited by the probability and therefore will never be ambiguous. So in this situation where we have equal weighting, I compute the 95% expected shortfall simply by taking the average of those losses that are in the 5% tail. See how I've done that? 1, 2, 3, 4, 5 out of 100 is 5%. 1 minus 5% is 95%. If we want the 95% expected shortfall, we delimit by the probability and take the average. So in this simulation, I get $35.19. If I wanted, for example, the 97% expected shortfall, I would take the average of the 3 worst losses, because that's the 3% tail. 1, 2, 3 divided by 100 is 3%, right? So here I'm getting a 97% expected shortfall. Here I'm getting a 95% expected shortfall in both cases. So here's the key distinction between expected shortfall and the conditional value at risk. In both cases, because I've made my average conditional on a probability threshold. This is 3% of the overall, and this is 5% of the overall. So that's the key to expected shortfall and why it's never ambiguous, because we've made this average conditional on or delimited by the probability threshold, in this case 1 minus the confidence level. Unlike the CVAR, the conditional value at risk, which would take an average conditional on VAR as the quantile. So if I say, what's the 95% conditional VAR as opposed to expected shortfall, what I mean now is I want the average of the losses conditional on the VAR quantile. The problem, though, is that, again, I have 3 valid VAR quantiles such that there are 3 valid conditional averages on the quantile. And so that's fine, but it's one of the reasons that we're lucky in the FRM, at least, that we really just use expected shortfall and we never have to deal with the ambiguity. Okay, so let me just add one variation that will really cement our understanding of this, and let me reduce the count to 50. Same parameters as before, my simulated column. Now it only goes back, in this case, 50 trading days as opposed to 100 trading days. So I guess that would be a situation where we've got maybe 2.5 months of trading data, something like that. And now, again, I'm still sorting my losses from worst to best in LP format. So among that 50, my worst here happens to be a loss of $63.74. However, because we've got 50 instead of 100 now, the implicit weighting on each of these is 2%. And so now the question is, what is the 95% expected shortfall? Well, I can't do the average of the worst 2 losses because that's taking an average of the 4% tail, and therefore this is the 96% expected shortfall, and I can't take the average of the worst 3 losses among 50 because that is the 6% tail, and this is giving me the 94% expected shortfall, right? If I just do averages here, I'm getting 96% expected shortfall. Here I'm getting 94% expected shortfall, but I want the 95% expected shortfall. Could I just average between these two values? Well, not really. We want this to be a true conditional weighted average so that we would take this value multiplied by its weight, this value multiplied by its weight, and now you can see so far I've got 4% of the tail. I want 1 more percent. So I just want 1% of this value. See how it's a weighted average? And then I sum them. If I just stop there, I'm getting an unconditional average. So I have to divide by that 5%. And now here, I have taken a true conditional average of that 5% tail. Happens to be $50.11. So those are discrete cases, but of course we have continuous distributions as well. So here's the normal distribution. And in the case of the continuous distribution, we don't really have the ambiguity problem. But here's the equivalent expected shortfall as a conditional average given some confidence level. I have here illustrated a 95% expected shortfall. So again, a probability threshold here, you can see is given by the integral, and I visualized it here in red. So this is a standard normal, and if we want the 95% value at risk, it's probably, you're probably already aware. You can see that's illustrated. Let me get rid of that right here by the 1.645. That's the quantile associated by a 95% confidence level, so one-sided. And then in red here, I have the area under the density distribution for the standard normal. And the 95% expected shortfall, then we won't in continuous distributions have to deal with any of this ambiguity, but it's going to be the same conditional average. So what we're doing is we're taking a weighted average conditional on the values in excess, or the losses in excess here, of 95%. So it's a conditional average, a weighted average of the area here as illustrated by red, conditional average of the area and the tail. So obviously, by definition, it will need to be greater than that quantile of 1.645. I have an old video up on the channel that goes into this in more detail, but for the normal distribution, it has a very convenient solution for us. We just take, here's my 95%. It's actually just the PDF, that's the probability density function, divided by alpha, or significance being 1 minus the confidence level. So the 95% expected shortfall, which we do expect to be greater than the quantile 1.645, is 2.063. So that's the weighted average value, conditional on us being in the 5% tail. If we go out to 99%, here's our familiar var quantile, 2.33 approximately. But if we take a weighted average of all of the values in excess of that 99% threshold, or the conditional average of all the 1% tail, we would get a 2.665. So these are quantiles, not probabilities, but they are losses. In other words, these are losses if we end up in the 1% or 5% tail. So that's the expected shortfall. If the video is helpful, subscribe to the channel and you'll get my next video. Thank you.